name is Lennartsson, and I'm a research manager in Kvaser. And this presentation is about CAN-XL, which is the next generation of CAN. And I will talk a little bit the real-time performance, how CAN-XL also makes efficient file transfer. CAN-XL is based on CAN and CAN-FD. So we start from the 30 years of experience, and CAN-XL is just an improved version of CAN and CAN-FD. We will see some benefits that is suitable for file transfer, and CAN-XL has also improved the driver circuitry, so we can increase the bit rate a lot. So the first part here, I will go through a number of slides where I describe the difference between the two different versions: classical CAN, CAN-FD, and CAN-XL. So what you see here in the bottom is a comparison with the classical CAN, CAN-FD, and CAN-XL. And as you can see here, when we go from classical CAN to CAN-FD, we get some more information into the frame. What we have here, all three frames are using only 1 byte. And when you go to CAN-XL, you see there a lot more. But again, we will see later that we can increase the bitrate a lot on CAN-XL, which will mostly compensate the longer frames, which is not as long as you can think. So the good with CAN-XL is that it works identical to CAN-FD and classical CAN at the start. So we have in the beginning starter frame, the priority 11 bits, and the remote request and IDE bits, and which are both are dominant. CAN-XL doesn't support remote request, which is not supported by CAN-FD either. So and this part is now mostly intended to be used for priority of the message. So the priority thing is the main thing that makes CAN real time, because if you have 100 messages and they're have correct priority order, 100 messages can be sent at the same time, and the CAN bus will secure that all 100 are sent in the correct priority order, which is very simple and efficient way to get real-time performance. So then we look into how we can distinguish the different versions. So classical CAN had a reserved bit here for classical CAN, which is always sent dominant. And when CAN-FD was introduced, it will use this reserved bit. So this will be flexible data format indication bit, which is recessive. The problem here for classical CAN is that this will tell classical CAN that this is a new version, but classical CAN didn't have any procedure to handle the unknown pattern that would follow this FDF bit. So the classical CAN will, when it detects this bit recessive, it will send an error frame indicating, I don't understand what you're talking about. When it comes to CAN-FD, they introduced the reserved FD bit here after the FDF bit. And again, when XL comes here, this will become recessive. And when the CAN-FD detects a recessive bit, well, CAN-FD cannot either understand CAN-XL, but in CAN-FD, there's a process what you can enable, which makes the CAN-FD controller ignoring all bits up to the end of frame. So the CAN-FD bit cannot interpret the XL frames, but it will just ignore what's happening here until it comes to the end of frames, where we will rejoin the communication for the next transfer. And CAN-XL has the same function, so the reserved XL bit here. So if there's a new generation here, it will do the same. It will ignore everything that's behind here and rejoin at the end of frame. So if you have, today we have 3 different CAN controller types, and classical CAN, of course, can be received of all of them. When we send CAN-FD frames, the classical CAN frames will send errors, but of course, both CAN-FD and CAN-XL. So the CAN-XL controller can handle both CAN-FD and CAN. So when we send a CAN-XL frame, again, classical CAN with an error frame, CanFD will just ignore the frame, and it will be received by the CanXL controller. And future protocols, CanFD and CanXL, can handle this just by ignoring the future CAN versions. In CanFD, we introduced a bitrate switch, which is to increase the bitrate. The problem is that the arbitration here, the priority thing, it depends on delay in the system. So it has limits. If you increase the bitrate, the bits get shorter and the cable length will get reduced. And if you want to keep the priority, which is essential part of the CAN. But after the arbitration, where we have only one sender, then we can increase the bitrate. And in CanXL, is the bitrate switch looks more complex, but it's much simpler and more efficient, because between this DH2 and DL edge, there is an edge which will synchronize the sample point in the receivers in very efficient way. But in CanFD, the decision was they made a hard synchronization here in FDF bit, and the sample point was the bit rate switch occurred in the sample point in bit rate switch bit, and you had a clock offset here depending on the module, which meant that the bit rate switch has some phase offset between the different units, receivers, and the transmitter, which made the CanFD more sensitive to oscillator tolerances. So this is one reason to switch to CanXL, is the very efficient and precise bitrate switching. And the second problem with CanFD is that the bitrate switch is at the sample point, because different receivers could have different sample point location in the arbitration bits, and that if they have different sample points, you will get a phase offset between different units, which can cause problem when you have very small data bits here. Again, by switching at the edge here, you don't have this problem in CanXL anymore. So then we come to the data length code. The classic CAN only support 0 to 8 byte, and if you send DLC 9 to 15, it will still end up only 8 bytes. So those numbers are ignored because it will stick to maximum 8 byte. So CanFD use this safe indication system here to make a switch. So you have the 0 to 8 byte, but the 9 will be 12 and 15 be 64. So you can have a number of different data length code. Of course, this is a problem, because if you want to send 25 bytes, you have to switch. They don't fit in 24, so you have to use 32 bytes lengths, and you have to end up with dummy bytes. And this problem is solved also in CanXL. So here you have 11-bit for the DLC, which means that you can have any number of bytes from 1 to 2048. So you can match. So if you want to send 25 bytes, you just put 25 bytes in it and no more. The problem here is, of course, that if you go to 2048 byte, the frames will be very, very long, even if you increase the bit rate, and that will occupy the bus and it reduce the real-time performance of the communication. It looks very long here. This is because added to the DLC, there has added additional protection of the data length code. So there is a stuff bit counter and a 13-bit CRC that protects from start of frame up to the stuff bit counter here. And that is necessary because the theory of Hamming distance is only valid for the frame CRC if the data length code is correct. So it's very important to have a correct data length code to make sure that you can prove that the farm CRC actually have Hamming distance 6. So that's why we have to pay for this 16 extra bits here, is to secure the Hamming distance 6. So in CanXL, we know that we need some support for the higher layer to make life simple. And there is 6 byte included here. If you make small system and doesn't know demand support to higher layer protocols, you can actually use those 6 bytes for data. Or you can redefine here which fits you, because those bytes are not perfectly hard designed into the CanXL controller. So let's see what they are doing. So the SDT, Service Data Unit Type, is very similar to what you have in Ethernet type. So this here would indicate what you actually have stored here. So you can talk about there's indication in this CIA 611-1, for instance, that you can have can open, which means that you have can open information, or it says J1939, which means that you have J1939 information here. So this is a data content type switch, so to say. There is also simple extended content, just 1 bit for simpler. And actually, I have not seen any specification how it should be used. The virtual CAN ID, CAN network ID, is defined for Ethernet tunneling, and that's understandable, because this is very much coming from Ethernet 802.1q, where you describe the virtual LAN. So this is something we have supposed to be used similar to the VLAN type we have in Ethernet. The most important thing that will probably be implemented in all CanXL control is this part. So this is a filter byte for previously in classical and CAN controller, we typically has a filter that can be applied on the CAN ID to say that if you have a matching here, the CAN frame will be received, otherwise it will be ignored and generate no interrupt for the software. And that filtration combined with selecting good priority is complex. So the intention now is to keep those 11 bits for priority only, and the filtration will be down here. So you will probably see here that the J1939 CAN ID, 29 bits, with PGN, source address, and destination address will be placed here. So that means that if you put the destination address in this byte, you can set a node number here matching this address, which means that you only receive frames where you have a destination address that is identical to your node address. So then you have 1 byte of data. This is the important thing, and we have all described the difference between the 3 types of CAN controllers. And in the end, we have a CRC, and you can see there how it's not linear, because we needed a CRC 15 to protect our 8 byte in a classical CAN, and we had CRC 17 to protect of 27 bits for protecting CanFT. And with CanXL, which actually have 2000 bytes, we only need 32 bits to protect the data and get the Hamming distance 6. Then we come back, we have a different bit rate, and when we come here, we need to switch back. So we have a pattern here, 2 recessive bit and 2 dominant bits in the data rate. And this gives you a good edge here, so we can do the switch from the data bit to the arbitration bits here. In this view, they have the same length, and of course, those bits can be much smaller compared to the arbitration bits. Nevertheless, when you reach this edge, there is a mode change. So CAN-XL support special CAN-XL drivers that will actually run in at a higher bit rate with push-pull instead of the usually dominant recessive bits, and that makes the signals much better and much more insensitive to ringing and things like that, because the energy is very symmetrical. You have a number of bits here, and we end with the recessive bit here before the end acknowledgement bit. So all those bits is here just to get some more edges to get the acknowledgement slot more precisely into the communication, and also make it easier to enable the CAN-XL controller to find end of frame pattern, so they can join in sending the next message here in the end. And again, when we come to the end, as it started the same with a priority, and it ended the same. So all protocols are the same. And those 7 bits here, as I said before, even if the FD doesn't understand CAN-XL, it understands the end of frame. So when it detects the end of frame, it can synchronize back and start arbitration with all nodes here for the next frame to start. So in the next section, we'll talk about a little bit more about the new CAN drivers. So we have the new CAN driver is called CAN-XL SIC, Signal Improver CAN driver. And due to this mode switch, where you go from dominant recessive bits into push-pull bits in the data rate, you probably can get to 30 megabit per second in a good network. The SIC, Signal Improved Controller, that already existing for FT, you can reach 10 megabit per second. And the legacy CAN drivers in the CAN-FD, you can actually go to 4 megabits per second with those drivers. But even if you switch to the CAN-XL SIC or the SIC drivers, the cable layout will still limit you have to design your cable layout very carefully to reach 20 megabit, and to reach more up to 30 megabit will be demand very limited drop lines and probably limited length of the CAN bus as well. So the main limitation is not the driver, it's the cable layout. And in general, it's the impedance variation that limits you. And the important thing that cause impedance variation is long drop lines, and the drop lines close together, and EMC filter in the nodes, which also will cause reflection due to the inductors and capacitors in that part of the interface. So again, yes, the drivers can help you increase the bit rate, but again, in the end, it will be the cable layout that sets the limits. And next, I will just make a short comparison of how CAN-XL is according why you should stay with the CAN-XL in place of replace it with the Ethernet. First of all, it's easy to migrate because CAN-XL in the beginning behaves exactly as classical CAN, and you can use the CAN-XL controller in a classical CAN network. And if you don't change the bit rate, they will work the same. And CAN-XL, this means that a CAN-XL can rely on 30 years of experience in your development department and service organization, and your supplier of products. CAN-XL, the main reason the CAN-XL was invented was to support TCP/IP in Ethernet in a simple way, and especially to send Ethernet frames without fragmentation. Of course, CAN-FD can send Ethernet frames, but if you have 1500 bytes, you have to chop them up in a number of 64-byte frames. But with CAN-XL, you can take the complete CAN Ethernet frames, put it into CAN-XL, and send it, so you get unfragmented TCP/IP Ethernet frames. And CAN-XL is actually more efficient than Ethernet because it has less overhead and more efficient. And again, if you go do a real-time system, CAN is designed for real-time system. If you go for Ethernet, you also have to implement time-sensitive network or other solutions to secure that your Ethernet system is actually a good real-time system. Another reason to stay with CAN-XL is instead of go to 10 megabit Ethernet is that CAN-XL also support 10 megabit per second. And actually, the main thing here is that, and the problem with Ethernet today, it can only support 10 megabit or 100 megabit. And 100 megabit is almost impossible to use on the drop line. It's only suitable for point-to-point. But CAN-XL can easily, proven from Detroit, as you see in the first presentation here, where we actually went to 20 megabit per second, and with the 20 meters and 8 nodes connected to it. So the good thing with CAN-XL is that you can select for any bit rate up to 20 megabits, which is double rate compared to Ethernet today. And this makes it possible to actually match your cable cost layout by using a bit rate that match your bandwidth need against the cable layout and the cost of the cabling. So what are Kvaser doing here? As I said before, we have developed the CAN-XL IP. We was using it in Detroit Plugfest with a great success. The main problem today is that Bosch don't provide a reference module, as far as I have seen, which means that we need to do the real hardware verification at CNS in Wolfenbüttel, and their test platform should be available in the beginning of next year. So the final hardware will not be available until next year. But though we had no problem to communicate with the Bosch IP, neither at the Plugfest in Detroit or at an office. So we can send and receive CAN-XL frame without problem already. The second problem we have is, of course, that those long 2K data frames will demand a new driver software to handle those longer frame efficiently, especially if you receive a couple of 2K frames and suddenly you get high priority 8-byte frames, and because then you don't want those long frames in the library to be blocked by the longer frames. You will like to have a CAN-lib here that actually can provide the CAN frames as high priority as fast as possible. So we don't have any hardware today, but you can also always contact us for discussing hardware. They will be provided on the NDA because we will need to have a direct contact with the customer, so we can upgrade and update both the hardware and the software to make the test results we will get in the future.
There's a question in the chat now. How much transceiver support CAN-XL?
Well, CAN-XL actually you can use any CAN transceiver existing today on CAN-XL. The only limitation, if you use the standard old legacy, you will stay at 4 megabit, and if you use the SIC that is designed for CAN-FD, you can go to 10, but to actually go to 20, you need to buy the new, still not available CAN-XL SIC drivers. So again, you can use the CAN-XL technology with the old drivers, but so the bit rate still is limited by the cable layout and the selected CAN drivers.
Yeah, so I assume it was. So in general, I think if I remind myself on the presentations given by Magnus Held from Infineon, you have a high scalability with regard to the physical layer. So as Kent already said, you can attach in principle any transceiver to the KNXL controllers. But of course, this may have some trade-offs then to the communication speed that you may that you can achieve at the end of the day. So if you really want to go for these 20 Mbit, as Kent has presented, you need the dedicated KNXL transceiver. And Kent, I think from NXP and Infineon, there is something in the pipeline. So at least from NXP, I have seen on the embedded fairground some prototypes. Infineon maybe a little bit later. So at the end of the year or beginning of next year, I think there will be something, isn't it?
Correct. I have those CAN-XL SICK drivers, but I get them directly in my hand from NXP. There's not even a data sheet. But they work. They work. But I don't think they're available. You need a direct contact with NXP or Infineon with the right person. So if you go to the sales organization, I think that you will not find them.
So that's good if you're a CAN Automation member, so we have some direct
contact. Yeah, I mean, those plugfests really means that you meet those people who actually have access to the latest technology.
Okay, thank you. We have a next question from your colleague. So you mentioned KNXL speed could reach 30 meters. Is it practical or theoretical?
If it's practical, a question, because again, well, in Detroit we run the 20 megabit, and you could see there in where you presented the noise in this graph that we had very low ringing even at 20 megabit per second. So I think 30 megabit is quite practical. But again, in the end, sooner or later, you will reach a drop line of 0, which means that the CAN driver almost have to be soldered to the bus line. So it's only a question of how much drop line you can take.
Does she mean meters or megabits?
No, as in Detroit, we had a drop line, I think, of 20 centimeters. And if you reduce the drop lines to a few millimeters, then you will not get any impedance variation. So you will get very, very little reflection when the signal hits the node. So it actually is a question of the practical. The question, how short can you make the drop line in practical? Because you need a connector. Otherwise, you need to wire the bus line into the node and pass by the CAN driver and then out again.
Yeah.
So you get a continuous, and you need to keep the impedance, cable impedance within this path into your electronics. So it will be quite challenging for the engineers to do the routing of the wires.
Of course. Maybe to complement your answer. So with regard to this Plugfest, we have an entire report on in the previous CAN newsletter. So we have a publication, a CAN newsletter, that is online, available. You can get it from CAN Automation's website. And there you will find a report. You will see which kind of topologies have been tested. And maybe there's also a picture from Kent, could be attended there. So there you can read and remind you on some details if you're interested.
So I think what the question is that I would say that if you use CAN-XL SICK drivers, you can at least increase the bit rates double. So if you have, maybe it's hard to say. You can increase the bit rate a lot if you go from, especially if you go from legacy CAN drivers to the SICK drivers. You can actually double the bit rate, go from 4 to 8 megabit is no problem. And I guess going to the CAN-XL SICK drivers, you probably can easily go to from 8 to 16 on the same network. So more or less you can say it's a doubling. So you go, every time you switch CAN driver technology, you can double the bit rate and still have the same signal to noise ratio. And actually, if you do EMC test, just going from legacy CAN drivers to SICK CAN drivers, even if you go in emission, almost every emission disappear if you go from legacy CAN drivers to the SICK CAN drivers in EMC test.
That's one interesting thing that we have figured out. So I have mentioned in my talk, it is a new working group, large network topologies, starting with CAN-FD, but also having CAN-XL in mind. And when we're talking about bitrate and how much we can achieve, we have always, as Kent already touched this topic, always to have in mind which kind of topology do we have. And we have seen in very large, that some people want to use CAN-FD or CAN-XL in very large topologies. And there, of course, we have to slow down a little bit. And we see some effects, not only the ringing, but also some frequency-dependent damping that is a kind of limiting factor, which kind of speed you can achieve. And there, somewhere at about 2 Mbit or so, it had been a threshold when you want to go to 250 meters or something like that. And this seems to be similar for CAN-FD as well as CAN-XL.
Yes, if you go long distance, it's the damping or the loss on the cable, and there if you go to SICK driver, it will be improved a little, but not that much.
Exactly, it looks quite similar. Yeah.
Yeah.
Okay, we have another question. Could you please share if there are already any tier 1 or car makers who plan to use CAN-XL with their products? So I think at least we can say that this entire initiative is based on an impulse from Volkswagen. So they want to have it for their platform. In which brand it is used then, I don't know. Ken, do you have some further input?
No, so it's the French and some German interest. I haven't seen. There's some interest from US and China, Japan, but they haven't officially said that they will go for CAN-XL. As far as I know, I haven't seen that anyhow.
So, but we are anyway on an early stage. But as far as this is the current indication. So I think we have answered that one. We have another one in CAN-FD. We talk about suggesting all CAN-FD issues using same sample point settings. Is CAN-XL have the same requirement? No, but Kent, you have already explained, but please repeat.
No, you don't have to. It's not still it's suggested to use the same sample point in all ECUs connected to one common system. But no, CAN-XL is for CAN-XL, it's doesn't affect it more than it's not a good idea.
So then, thank you very much for being with us. Thank you to all the speakers for supporting, and also to Honke with regard to assisting us in organizing the event. And well, if you're interested in, we will have a next activity here. We are talking about CAN OpenFD host controllers. We will have a small workshop on a virtual base, web-based, and we want to talk what are requirements on host controllers and how can we meet them in form of specifications. So we are currently updating SIA 1302 at Canon Automation, and we are asking for the input from our member space as well as from any CAN users. What do we have to consider for CAN OpenFD host controllers? Furthermore, if you want to see what's offered by Canon Automation, seminars, webinars, technology days, directly on our homepage of Canon Automation, can-cia.org, you find all the valuable information when our next events. So I'm looking forward meeting you once again on one of the other events that we are offering on other occasions. If you have any questions, any challenges with regard to CAN, then please feel free to contact us. You see here the contact addresses, and we are very willing to assist you. Yeah, all the best with your CAN-based projects, and hope we see you soon. Thank you very much.